everyone. So let's start. I'm Kevin Tian from Intel Corporation. Today, I and my colleague Shaopeng will introduce the post-copy NIC migration on pass-through device. I will first introduce the high-level design, and Shaopeng will introduce the NIC-specific implementation and also the performance data. Most of the data here actually was done by my colleague Zhao Yin, but she cannot make for this conference, so I will present for her. So NIC migration, I think most people are familiar, right? Basically, just lively migrate the VM state between the server loads, including the CPU state, memory state, and the device state, also including the VM configuration info. Today, I think in cloud or data center, this has become the cornerstone capability, right? Either due to the load balance requirement to meet the service level agreements, or due to infrastructure maintenance requirements. NIC migration is a basic capability to meet those requirements. When we talk about NIC migration, I think most of you know that the memory state occupies most of the time. Today we have two approaches. One is the pre-copy, the other is the post-copy. So when we talk about the pre-copy, it just means that we will copy the guest memory when guest is still running. The entire guest memory will be copied once to the target machine, and then the hypervisor will iteratively copy the dirty page to the target. When the remaining dirty page reach a threshold, or when hit a timeout, the pre-copy phase is completed. And then the VM is stopped on the source machine. The CPU state, device state, and the remaining dirty page are copied to the target machine. And then migration completes, resume the VM on target machine to continue execution. Post-copy is in another way. There's no memory copied when the VM is running on source side. Just stop the VM immediately on source machine, and then copy the CPU state, memory state, to target. After the VM is resumed on the target machine, then the entire guest memory is copied from the source to the target target. That actually involves two memory copy. One is source will actively push the memory to the target side. The second is when there is a vCPU fault happens, the target will proactively pull the memory from the source side. So compare pre-copy versus post-copy. Pre-copy is more mature and reliable. If there's any problem happens in the migration process, because all the state are still on the source machine, you can just exit the migration process and then resume the VM. It just works. But for post-copy, because you are recovering the state when the VM is running, so if there's anything happen, even the source side doesn't have the latest state. So it will be more challenging to recover from the migration failure. But on the other hand, if you look at the post-copy, it's more predictable and also faster because for every guest memory, you only need to copy once. You don't need iterative, dirty page tracking. That's the main difference between these two models. So here, look at the detailed flow of today's post-copy NIC migration without a pass-through device. So first, I think source will send a post-copy advice command to a target. When receiving that command, one relevant action is to discard all the memory in the target side. This can make sure that in the future, when there's a CPU access happens, it will trigger a page fault to do the pull. After that, the CPU and the device data are migrated, and a post-copy listen command will be transferred to target. When receiving this command, target needs to create a user fault FD and register a range of the memory that QM will want to monitor to handle the user fault. When receiving the post-copy run, then the VM is just started. After that, just as I mentioned earlier, the source side actively push pages to the target. But in case any vCPU page fault happens, then the target will also actively pull the page from the source side. After the process completes, after all the memory is copied to the target, then the whole process is end. Then here are the challenges with pass-through devices. The first one is, because the device is pass-through to the guest, the host has no insight into the device state. So how can we migrate the device state? That's the first challenge. And the second challenge is, today most devices don't support the DMA page fault. So there's no chance for the target hypervisor to fault at the pool like the VCP access. Right? If you don't prepare the page before DMA happens, that will trigger a VTD page fault. It may either lead to driver not working or maybe even panic situation. So talking about the device state, I think first I want to briefly talk about the definition of the device state. The actual definition is vendor specific based on different device. It may include standard PCI resource, including the PCI configuration space, including the MML registers in the MML bar, the MSI, MSIX internal information, etc. Those are standard way you can just try to read from the PCI interface. But there are also some vendor-specific resource. For example, there might be some hidden state on this device, which cannot be read through the MML interface. Or there may be some state just maintained in the PF side when the VF trying to use a doorbell to get the PF service. So that will require some cooperation from PF driver. But anyway, I think before applying this model, you need to study your device carefully, whether this device can allow the host to save and restore the state. We know there are some devices which even don't provide the interface to dump the hidden state, and it's not qualified for this model. Another point is, besides the device state, there may be some pending descriptors when migration happens. Those descriptors are submitted by a guest driver, but has not been completed by the hardware. So for all the pages referenced by those descriptors, we want to migrate their memory pages in the stop phase. But that state, I think, the size of that page is device specific. For example, for the network card that in your experiment, it's just dozens of pages. But if you talk about the GPU, there might be hundreds of megabytes. So that's quite different. So once the device is qualified for this model, we basically can create a wrapper driver on the host side to poke the device state. And how this can be done, there could be two options. One is to just use the VFIO MDev by wrapping the device into a single MDev instance, as in just use the MDev operations to do the mediation. Of course, we can also just hook to the VFIO PCI ops. I briefly discussed about that this morning. There's still some discussion. But once we have the state in place, then we can further use the migration region on top of this device to pass the information to the user space to allow the QEMU to set the device state through this interface. So second challenge about the fault. Since the device doesn't support the DMA fault, we have to find a way to pre-fault. When I say pre-fault, that means we want to capture the potential fault condition before DMA happens. So it basically means that we need to trap any guest operation which may cause DMA access, and then decode the operation to find out which pages may be used for DMA, and then notify those pages to user space to pull the pages in place, and then resume the operation. Later, when DMA happens, then those pages already mapped, then that should be fine. Of course, how to identify the DMA pages device specific? You may trap the MML access or scan the workload descriptors. There are multiple methods, just study the device. One requirement for pre-fault is that we need the capability of dynamic mediation, because we don't want to trap those things all the time, because it may need to interfere with the data path. So we just wanted to enable mediation only when migration starts. So that also requires some change in the current, VFIO mechanism. That we need a mechanism to turn on the mediation only for migration, especially for the regions which are marked as the mmap. And when migration completes, we will need to re-enable the pass-through. Today, we just introduce a mediation bit mask in the migration region to indicate which region should be dynamically mediated. And today, we define just per MML region, but in the future, we may introduce some sparse capability to allow final grained control. Yeah. So the last piece is how we send the fault information to user space. Before that, we look at the existing model, the fault and pool. This is based on the user fault FD introduced in 2015 by Azure. So when there is a page fault happens, the host MMM captures the fault and sends the notification through user fault FD to QMU to request a page. QMU will pull the page from source side to the target and then resolve the page fault. The last step is done through a user fault FD command called UFFDIO copy. This basically combines 3 tasks: allocate the page, copy page, and wake up VCPU. So the ideal approach is to reduce the same interface. Once we identify which page might be potentially used for DMA, we can use the same interface to pass information. Just like this, right? When there's a trap happens for whatever operation, the mediator scans the operation to find out the DMA page, and then use get user page to trigger the MM check. If there's no mapping, the MM will send the page request just using the same interface. We get the page copied from source. And there's a little bit of trick for the last step because before wake up, we want to also apply the VFIO map. So basically, we want to separate the page copy and the VCPU wake up. Today, the user fault FD provides a non-wake up version, the UFFDIO copy with don't wake. We first do this, just copy the page and then do VFIO map and then do wake up. So use this way, we can interleave the VFIO map in this final phase. But the main limitation with this approach is the address in the guest structure is the IOV address, is the DMA address. Its actual meaning depends on whether virtual MMU will be enabled. If the virtual MMU is not enabled, it's equivalent to GPA. If virtual MMU is enabled, it's actually a guest IOV. There are 2-level translation. The problem is, at this step, before we do get user page, we want to find out the host virtual address. But there's no mapping existing in VFIO yet, so we cannot get that information. If there's no virtual MMU, ideally we can get the mapping from KVM because it's just GPA to HVA translation, although we introduce some KVM dependency. But if virtual MMU is enabled, how can we find out the GIOV to GPA translation? That's a problem. That knowledge currently only exists within QMU virtual MMU. So that problem makes it difficult to use get user page. The second limitation is about device local memory. If we also, for some device which have a large local memory, if we also want to do post copy, how we can apply that model to the user fault FD, that may also have some challenge. So in reality, we just use some VFIO specific approach. We just build a new notification interface in the migration region structure. We introduce a new event FD to notify user space. We extend the data region to carry the pre-fault information. So once the mediator identifies the DMA pages, we use this interface to pre-fault to the QMU to pull the page back. After page is back, we still use user fault FD to do the final allocation and the copy. For the CPU page fault, it still continue with the user fault FD. That's just the same path. This is not the final conclusion. We are still exploring whether we can leverage the user fault FD for the same purpose. But at least for now, seems this model better fits the IOV-based pre-fault and can be easily extended to device local memory in the future. Okay, that's all about the high-level design. Now welcome my colleague to introduce the NIC specific thing.
Thanks, Kevin. Hello, my name is Shaopeng from Intel Network Division. Today I will share a case study using NIC pass-through for the post-copy line migration. Here we use Intel XXV710 NIC, which is a 25G version of widely used Intel 10G NIC with RDMA supported. The VF interface is compatible with 10G NIC and the later generation, for example, Intel E800 NIC. Currently, the prototype puts the VF in reset state before migration, which is a quick workaround to avoid the copy device state. But for the long term, we will follow our mentioned direction by doing the state save and restore. It tracks DMA pages by scanning ring descriptors in target machine. It mediates the guest writes to the ring tail register and pull the DMA pages from the source machine before sending to NIC for DMA read and write. Here is a system block diagram. In the left side, this is the source host, and in the right side is the target host. For both hosts, we separate them into three parts: user space, kernel, and hardware. And we also mark the important modules with blue color. That is the line migration module in the QMU, and the dirty page tracking, and the post-copy ring synchronize module, etc. in the kernel PF driver. Pre-copy and post-copy share the same framework for tracking DMA accesses. Pre-copy did it in the source, post-copy did it in the target host. We implement the MDEF device model in PF driver, which manages ring mediation and get set VF configuration data. This is based on Intel Unified NIC Interface, AVF, which could easily be extended to support migration across different generations of NICs. Of course, they're mostly Intel NICs. We measured the performance using a memory-intensive workload with 2 GB guest memory and 1 10 Gbps migration bandwidth. Here list 3 benchmarks. The first one is total line migration time. Pre-copy used 128 seconds, and post-copy used only 3. The second is the VM downtime. Pre-copy down 138 milliseconds, post-copy only 17. The third one is network downtime, which means VM lost network service. Pre-copy lost 450 milliseconds. Post-copy lost a little bit less, 420. Both include about 300 milliseconds of device reset and switch configuration time. For the post-copy, it has about 100 milliseconds of overhead, mostly contributed by VFIO DMA mapping, etc. We already optimized this overhead from previously about 1 second by making the higher priority for the real DMA pages in the mapping process. This design and the performance number are based on the initial prototype. In the future, we will continue to explore in several directions. The first one, remove reset. Second, extend user fault FD and create a VFIO-based interface. The third one, IOMMU mapping efficiency. That was the 100 milliseconds we just discussed. And the fourth, huge page. The fifth, device local memory. And the last one, we will extend to other NICs and device types. For example, storage. For the source code, we will send out the pre-copy RFC firstly, very soon, I hope, and then post-copy. Okay, that's all for our presentation. Thank you. Any questions?
Thank you. Just go back to that performance slide. I think that this interesting data, but I would say the first diagram might be a little bit misleading because the definition of line migration is different between pre-copy and the post-copy, right?
I think the definition is when you start the migration command to the migration completes, right? Their starting point is different, but that's the difference.
Yeah. Okay. If we think that's the way the definition, then I think there might be another benchmark you want to try is you want to try the memory bandwidth testing across the migration, right? Because after the migration, the memory benchmark, the bandwidth testing might suffer a little bit, right, as the post copy.
Yeah, we can have a try. Yeah, thank you.
Thank you. That's an interesting set. I'm curious about the downtime shown here. The switch configuration, well, how much of the time do you think is the device reset and how much do you think is switch configuration? Because that's a very large number compared to those two.
Yeah, that's the place we want to improve later.
Okay.
And roughly estimate was we spent 100 milliseconds for the device reset, and we spent 200 milliseconds to wait the traffic really come back, because the switch needed to have the MAC address in this port and switch that port. But that one, when we finish the integration with the OpenStack, etc., maybe make it better.
Was that measurement on OpenStack or was that QEMU by itself?
No, I think this is not related to the QEMU. It's mostly related to the network itself.
Okay. So the other thing I was going to say is you talk about how to get from IOVA address back to HVA. I think vhost user already has a mechanism for doing that. It has a cache of translations.
Yeah, actually we discussed that. We discussed with Alex, quite a lot. But Alex, okay. don't deny that. Yeah.
So, historically, whenever we try to save state of a software implementation of devices and then restore them, and we had to preserve that compatibility across different versions of QEMU, run into a huge number of problems. And we developed some solutions around that based on machine versioning. How do we prevent
so
that
in the
from
compatibility about the pass-through device, how we can detect whether they are compatible?
and then you're putting this stuff in, some of this in the kernel apparently, some of this in the hardware. I wonder how do you gonna prevent that?
Yeah, that's a good question, but I think similar to MDEV, right? Even for MDEV, previously we discovered Alex, how we can detect the two MDEV between two machines are compatible. And I think we have some interface to detect that. With MDEV interface, maybe we can leverage that for this.
Yeah, right now,
Yeah, I
guess
would
the
agree
answer is
it's a gap. Today we just detect the CPU machine type, but we don't detect the hardware part, right? That's
yeah,
different.
and you know, like it could be exactly the same hardware, just slightly different firmware versions,
Yeah.
or
Yeah, I think
sometimes you just buy, you know.
Yeah, I think that's an issue we need to solve before really push it to the real production environment.
And then, yeah, so my second question is, like, it's a little bit like the failover in that you start processing the ring and software. Failover kind of has an advantage is that it's independent of the specific hardware, so you can move between hosts which have different NICs. So what do you think about failover? How does this compare?
Yeah, failover, as I talked this morning, we may leverage a similar technique, right, to do that. But maybe that's not part of this migration stuff. Yeah.
Okay, one last question.
Hi. So one additional performance graph that maybe is missing is kind of, you talk about down and up, but it would be interesting to compare between the pre and post copy, what the impact is on the network adaptive bandwidth during that time. So with pre copy, the time it takes might be longer, but the interruptions might be less. And in post copy, if you keep having to fetch descriptors.
So sorry, I didn't quite get your question.
Yeah, well, I'm saying maybe a missing slide would be to show for the extent of the pre and post copy to show what the bandwidth is as a function of the time. So I mean, I wonder whether maybe pre copy the migration time might take longer, but the impact on the networking might be less. Maybe in post copy it might be shorter, but maybe the impact with networking is more severe. So so maybe the downtime might be shorter, but maybe the impact is longer.
Yeah, I agree. We still need to get more data from that part.
Okay.
Yeah.
Okay, thank you. We are out of time.
Okay, thank you.
Thank you.